Okay, welcome to lecture 3. First, apologies, you may notice the sound isn't as high quality as the other videos. My microphone is having some issues today, so but I figured the camera's microphone is good enough here, but I apologize for that. Today we're going to be doing our second sort of painful lecture about math. Once this lecture is done, and I don't think it's quite as painful as the last one, but I don't know, I'll let you be the judge of that. Once this lecture is done though, you will have all the math necessary to understand the rest of this course. Don't let it scare you, you'll have the rest of this course to digest it, and even without it you could probably get by pretty well. You'll see from past exams they're not terribly math heavy. So I really just want you to understand this so you can appreciate the foundation on which the theory is built. But you'll find most of the theory of this course can be done quite qualitatively and just using visualization capabilities of shapes and these kind of things, and not so much the math. Okay? Alright, but let's jump into this. This is some cool stuff if you can follow it, but again, don't let it scare you away. Alright, okay, so first we're going to talk about the Bernoulli Euler beam stiffness equations. Okay, so first of all, the most common flexible element is just a rectangular prism. Okay, it's an extruded rectangle that has some kind of width, length, and thickness h here. Where the width is b and the length is l. Okay, and you can see different values of these parameters get you different shapes. So here you have blade flexures on these top ones and these ones and this one, but you can also make b and h about the same thickness or about the same size and get your wire flexure. Okay, you can also shrink those to get nub flexures, and you can do other interesting combinations to get other flexures that are common. Like for instance, if B is really long, L is short, and H is short, then it can also be like a notch flexure, or kind of a hinge, right? And by the way, L is always the length that spans the distance between the two bodies that it connects, so like the ground and the stage, L is always that length. So if you connect these and make B large and H thin and L small, then you can see it'd be kind of like a hinge joint. Okay. So this is a very useful geometry to be able to characterize the elastomechanics of. Most of the time, it finds itself in wire flexures and blade flexures. Okay, but first let's understand some principles of mechanics here. Okay, so what is stress and strain? Well, stress very simply is if you take stress is essentially the forces in a body, much more rigorously defined. It's if you load a body F and divide it by its cross-sectional area, then you get the property of stress. You find out what loads are inside the beam here for an axial load. It's, of course, in units of newtons per meter squared, or pascals, right? That's kind of like similar to pressure. Okay. And there are stress tensors and all sorts of things, but really you just need to know the basic definition. Okay, and then strain, and by the way, there's a difference between true stress and engineering stress. True stress is when the cross-sectional area changes as it deforms, but we're just going to stick to engineering stress, which is you divide by the initial cross-sectional area. Okay, strain is how much it displaces divided by its original length. Okay, so D over L, according to this animation here. And these properties these values are very useful to plot, okay, because you can derive material properties from the material and not so much from the shape of what's being loaded here. So you could think of stress as kind of a force, and you can think of strain as kind of a displacement, but they're not quite those things, they're these. And if you plot the stress on a beam versus the strain, okay, then what you find in most materials, certainly linear elastic materials, that for the first little bit you get a straight line where the slope of that line is a material property. You know, if this was just force versus displacement, it would be stiffness would be the slope of that line. But stiffness depends on not only the material but also the shape and everything it's made of, or you know how its geometry and how its topology and everything. But you can make, if you take the slope of stress versus strain, then this is purely a material property, and it's called the Young's modulus. Okay, and you can think of it as like the stiffness of a material. All right. Okay, so what happens here, if you were to animate this picture here zoomed in on the atoms as it elastically goes up and then bounces back down along this straight line, is that each independent little atom gets stretched, and their atomic bonds kind of like behave like springs, and you know, as long as you don't break any of those bonds, as long as there's no you know, propagations or dislocations of those atoms, then they bounce back to right where they came from, and just goes back here, which is, by the way, why you know, compliant mechanisms are very precise, right? This is why they don't have you know, they don't generate friction, internal friction anyway, and hysteresis and things that are bad for repeatability, right? Now, of course, they do, as we'll talk about, but for small deformations, they effectively don't, okay? They're very repeatable as long as you don't stress them too far. Okay, but if you stress them to the point of yielding, this is the yield stress, okay? Then what actually ends up happening is, instead of this staying straight, it starts to curve off. It starts to not be straight, essentially. And what's happening when things yield is that you start stretching the atoms so much that the bonds break. And when the bonds break, they kind of dislocate and reform next to a neighboring atom. And that breaking of the bond does release energy. And that's why, you know, if you get a hanger and bend it back and forth a lot, you know, plastically deforming, it'll get very, very hot, and you can actually burn yourself. You know, so you know, heat is released, and it's kind of considered internal friction. And these atoms, you can see them dislocating along certain slip planes as they break and reform, and that's what's happening. That occurrence is a permanent deformation. Of course, once you break and dislocate the atoms, they don't just suddenly snap back. They remain permanently deformed. So what happens is plasticity occurs. And let me show an animation of this. You can see here it's elastic, but now you see these slip planes, these atoms, let's see, right here, start slipping and breaking, and then you get to this point, and this animation is showing you letting it go. And when you let it go, it does bounce back, and it actually does so, it follows a line that has the same slope as this, it's the modulus. And then when your stress or your force on it is zero, you can see there's some permanent deformation there. So it does spring back about this distance, you know, from down there to there. That's the spring back, but it remains permanently formed. That's what you see here. So you can see it right here. It's stretching. You can see it plastically deforming. Now we're going to unload it, and it comes back and it's at rest, but it's a little bit longer. It's permanently deformed. Okay, so it's important to understand how that works and how these atoms, as they break and dislocate, they're releasing kind of internal friction, and they create problems, right? They generate heat, and of course it's not a repeatable process. So the precision and repeatability, you know, dies off here. The other thing is that they will exhibit hysteresis. Okay, and hysteresis means it's now dependent on the history of the loading, essentially. Right? So if before you yielded, you're just going up and down, you don't ever need to know how many times it's gone up and down that, because if you're ever at this strain, you know you're at that stress. Right? And so there's kind of a one-to-one mapping. But once you yield and you drop it back down, say you pushed it all the way back and brought it back to this point and just kept doing kind of a loop, you'd need to know how many times you looped this, loaded it, stretched it, and then crammed it back in the negative direction. It's kind of going off the page here. But you can get it back to a starting point by plastically deforming it and do these loops. And what happens is you no longer know if you're at this strain, you don't know if you're at that stress or if you're at that stress. There's two, if you draw a line here, there's two stress solutions that it could be, right? And so you need to know where it is along the path and what its loading history was to know what state it's in. And that's why it's called hysteresis. And you can get these loops and things behave. If you loop it many times, you'll see it behaves differently, slightly differently each time. It does settle into one nice kind of loop, but you need to know how many loops have been done in the past, and it's not a repeatable process, so it's bad for precision. So you generally want to stay away from yielding, right? Okay, so that's yielding, hysteresis. That's just some mechanics there, a little review of precision. Okay, so now let's look at these principles in another way. So we just showed you if you have a rectangular prism and you pull on it along its axis with a force and it displaces a distance d, you can prove that the stiffness, not just the modulus, remember the modulus is basically the ratio of the stress divided by the strain, it's the slope, and from that you can very easily derive that the stiffness of something that's a rectangular prism is the modulus of the material multiplied by the cross-sectional area b times h divided by the length. And that will link the force to displacement. That is the axial stiffness. Okay? Again, very easy to prove just by knowing stress over strain is modulus. And using these definitions, you can prove this very quickly. Okay? Less easy to prove and beyond the scope of this course, but it's in classic beam bending classes that study beam bending elastomechanics, is that if you now take this beam, this rectangular prism, and you load it with a force tangential in the bending direction, and it displaces d, you can relate the bending stiffness that relates force to displacement, excuse me, is 3 times the modulus times the area moment of inertia, okay, divided by the length of the beam cubed, okay, where the area, or the bending area moment of inertia is b h cubed divided by 12, okay, where h and b are defined there, okay? And so again, I'm not going to prove that to you, but that's something you should memorize right on the insides of your eyelids. That's a very valuable thing to know in your life, that is the case, okay? Now, there's different kinds of stiffness, right? This relates force to displacement. What about force to theta? Because that beam will also bend a certain angle. It doesn't just purely translate and displace. It doesn't, it does translate. If you put a dot on there, it will displace, but it'll also rotate some angle theta. Well, it's actually interesting. You can also prove, and again, outside the scope of this course, that stiffness that relates force to theta is 2EI divided by L squared, where I is still this. Okay, so it's basically the exact same equation, except instead of 3 here and 3 there, you put 2 there and 2 there. Okay, which is interesting. And again, this stiffness is in units of newtons per radian, or just newtons, and this is in units of newton per meter. Okay? Okay, interestingly enough now, if you torque this in the bending direction, okay, this beam will also, say I torque it like this, this beam will also deflect. If you put a moment on it to bend it, it will deflect and it'll rotate. Okay, and if you then find the other stiffness, which is torque to displacement, okay, you see it's the exact same as force to theta. So going back here is force to theta, 2EI over L squared. This is also 2EI over L squared. That's torque to displacement. Okay, so that makes it easy to remember. And of course I is the same here. And then if you do torque or moment or couple, whatever you want to call it, to theta, then it's EI over L. Okay, so again, it's the same as this, except instead of 2 here and 2 here, it's 1, 1. So that makes it really easy to remember. So really all you have to remember is EI over L and then you have to know whether it's 3 times that raised to the third power, or 2 times that raised to the second power, or 1 times that raised to the first power, okay? So it makes it really easy to remember, okay? And of course, that all applies, and oh, by the way, this is in units of Newton meters per meter, or just newtons, right? And this is in units of Newton meters per radian, or just Newton meters, okay? Okay, so there's different kinds of stiffnesses there, and I've gone through all of them. They relate the 2 different kinds of loads, force and torque, to the 2 different kinds of displacement, linear displacement, angular displacement. And that's how you find it for rectangular prism. And notice it applies in the other direction too. You know, if I were to put the force going this way, and I looked at the bending angle and the displacement in the other direction, it's basically the same. And same thing with the torque. Instead of there, say I put a torque there, they'd be essentially the same equations, except you'd have to be careful how you used B and H, right? You'd have to swap them appropriately. Okay? All right, so the final thing, though, that we haven't talked about is what about, the first thing we talked about is force along the axis to displacement. And there's, of course, if you have a force, you don't have an angle, so it's just force to displacement. Here, we're going to put a torsional torque or moment or couple on the end. And of course, that doesn't result in a displacement either. That results purely in an angle. So instead of F equals EA over L times D, which is the linear stiffness, it's torque equals GJ over L times theta. So it's very similar. G here is the shear modulus, as opposed to the Young's modulus, E. J here is the polar moment of inertia, area of inertia, right? Instead of the bending area of inertia, and then L is L, right? It's a similar thing. So you can see these are pretty easy equations to memorize because you can see the analog. Okay. The trick is the polar, polar moment of inertia is actually quite a nasty equation. It's given here. If you look it up in textbooks for rectangular prism, or certainly online, you'll find they're actually wrong. There's a number of there's a very elegant, simple equation for J for rectangular prisms that's popularly used, but it's totally wrong. So, this is the correct one to use, okay? And will get you much closer in the ballpark than any other J. Unfortunately, it's ugly. Notice here this is a sigma that's adding up the odd numbers. It's n of 1, then 3, then 5, then 7, then 9, and it just keeps going, right? And you have a hyperbolic tangent function here, and it's basically all a function of B and H, okay, of the beam. And you can see that's the equation. You solve it by iterating. And just notice, even though this can go up infinitely large, it does converge very rapidly. So usually by the time n is 7, it's pretty much converged, right? So if you're ever calculating it, you don't need to do too many summations there. But it's important to note that this is true only when B is less than H, right? This is only true when B is greater than H, which is usually the case. The width is usually larger than the thickness. But if you have a scenario where you're sweeping the geometry or something, or maybe you've mislabeled it, if B is less than H, then it's the same equation, but you swap H out for B and B out for H in here, okay? And then it will be true. Okay, so those are all the different kinds of stiffnesses. In all, there's essentially a number of equations. I believe there's 10 equations that will characterize the full stiffness in all, 3 independent axes of this beam. If you put a coordinate system at the end, and if you plot all the different forces and torques and displacements and thetas in all these 3 different directions, you get a number of equations. And they can be captured in this 6 by 6 matrix. Okay? So, let's see. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's right. So there's 10 different components in here. That result in essentially 10 different equations. And you'll see here, the equations in this matrix, it would be otherwise a zero matrix, but the components that are not zero, that are plugged in, are essentially the inverse of these equations. So it's like if you take this whole thing and times it, times both sides by L over G divided by J, then it relates, tau is the input equals theta. And if you do that, if you go back and do all these, multiply them to the other side, you'll see we're looking at these. And the reason is because we're relating here, it's just easier mathematically to prove. If you times all the torques and all the forces at the end of a beam, we want to relate it to all the thetas and all the displacements. Okay? So, so if you have this rectangular prism and you ground the backside, remember, and then you imagine it attaching on the other side to another body, its length will be the distance between those two bodies, L, and then B is the width and H is the thickness, and usually you want B to be larger than H, okay, but we know how to deal with it if it ever gets smaller, okay, and we're going to define this coordinate system very specifically, okay. You'll notice that this coordinate system is right in the middle of the rectangle. If we were to look at that rectangle cross-section, the coordinate system is located not at the edge, not at the side, right in the middle, and Z is going out of the element and into the body it attaches to, according to this convention, right? And Y corresponds, it's perpendicular to the face where there's B, and X is perpendicular to this face where we have labeled H, okay? So for that coordinate system that we've carefully defined and given these parameters, you can relate if we put tau x, tau y, tau z, load the beam with any of those torques, moments, or couples, and then we load it with F x, F y, F z, load it with any of those forces. The question is, how does this point on the top of the beam move as far as theta x, theta y, theta z, and dx, dy, dz, and that's what these are. So here's the loads at the top there, and here's the resulting outputs. Okay, and since we're timesing these loads by something to get the outputs, that's why we switched all these directions. In this case, we plug in the output or the displacement, and here's the load input. So we had to flip these to then multiply the load to get the output displacement. Okay. Okay, so you can see all these equations are very familiar. They're just flipped, numerator and denominator flipped upside down. You might also notice some of them have negative or positive signs, and let me explain how that's the case. So let's go through it and explain this here. Okay, so here, I'm going to just stand up on the chair here. Okay, so if we take this and multiply it by the top row, take these loads, multiply by the top row, they should equal theta x. Okay? So, and let's think about it. If we do a tau x, okay, so imagine putting a torque or a moment on that x-axis right over here, okay, then we would expect and say always assume it's positive. This is positive tau x. If we put a positive tau x using your right hand about this axis, then we would expect a positive delta theta x also in that direction. And if you look at the equation, the bending equation there that relates tau to theta x, let's go back here. Okay, let's see. Yep, tau to theta x, it's EI over L, which we're going to flip this so it's L divided by EI times tau is theta here. For bending, notice this is the bending case, then you'd see this is correct. If you do EIX, and look where x is BH cubed over 12, tau x times that is that. And you think, well, there we go, we've related them. And we can make all these zero because none of them affect it. But then you see, well, this one's not zero. And you ask yourself, well, which one is that one? This one's Fy is the one that would multiply by that one. And apparently, it adds to this one to influence theta x. And would that be true? Think about it. If Fy was positive, say I put a load up there and I pulled it in that direction, Fy positive, with a force, and I times it by this, the equation that relates that, the bending equation, you would get a theta x component. Of course, it would bend that way, right? This beam would, if you put a positive F on that, the beam would bend that way. And that would be, you got to always use your right hand, that would be a negative theta x, which is why this equation goes to negative here. Okay, so remember, if it's positive Fy, it's pushing that direction, it's bending the negative direction that way, so you have to subtract it. And look at this. So if you have, here it is, for a bending force, pushing a force there, the theta, it relates F to theta, is 2EI over L squared. And in this case, we flop it, so it's L squared divided by 2EI times F equals theta. And we're going to put a negative, so see there it is, 2EI x, then L squared is on top. Put a negative there because it will be in the negative direction. Okay? And you can see the other things, tau y, tau z, fx, fz, none of them affect theta x, delta theta x. Okay? And the reason I say delta here is because it's only true if it's infinitesimally small. These are the Bernoulli Euler equations, and they're linear equations, they're simplifications, they only do infinitesimal displacement analysis. Once the beams deform a finite or large amount, the equations don't work anymore, right? They just relate force to infinitesimal displacement, okay? So it's like if you plotted force versus displacement, it would be the very first slope of the plot. It's the instantaneous first slope of the plot before anything ever deforms is what we're really relating in these equations. That's the stiffness we're talking about, okay? But for very small displacements and for pretty small loads, they're a very good estimate, okay? Nothing's deforming large amounts, it's just infinitesimal, essentially. And like I said, the only ones of these that affect delta theta x is tau x and Fy. The other ones don't, so they're zero, and this one's positive and this one's negative, so it can sort itself out. So you times out, that's the first equation. Now what I want you to do is go through all these other equations. There's 5 other rows. There's this row, there's this row, this row, this row, and this row. And times these loads into each of those rows and set them equal to their corresponding row here, and convince yourself that they do indeed, knowing those equations of stiffness, add up to these. Okay, so like for instance, this last one is all 0. The only thing that affects is Fz. We know that's the inverted stiffness. That's the compliance of a beam along the z-axis, and that would be delta dz. Okay, and so check me, make sure my signs are correct, make sure the equations have been flipped and they're in the right location, and everything's being considered. Okay, so you'll go through and you'll see that for this convention, what I said is z's, it's centered in the center, z's going up, y is coming out corresponding to b, x is going corresponding to h, that this matrix equation captures all 6 equations relating the 6 torques, the 3 torques, the 3 forces, and the 3 thetas, and 3 displacements. Okay, and it's all true for these things as long as b is greater than h, and if b is less than, as long as b is equal to or greater. If b is less than, then you just switch the h and the b in here. Okay, and so that should hold true for any rectangular prism for small loads relating infinitesimal displacements. Okay, so this is called the compliance matrix. Okay, remember, stiffness is what usually times stiffness by displacement to equal force. F equals kx, right? Well, compliance is the inverse of stiffness, or 1 over k, and it's what you times force by to equal the displacement. And so in this case, we call this the compliance matrix C, because we're timesing like our loads by it to get the displacement. Okay, if we were to invert C, this is C raised to -1, just like you would take C and 1 over C is K, or 1 over K is C. You invert this, but you do it with matrix inversion, -1, raised to the -1, and that will be the stiffness matrix for this particular beam. Okay, according to Bernoulli Euler equations. Okay, and now by the way, these equations will only hold true when this is truly acting as a beam, meaning it's length is something up to the order of like 10 times longer than its B and H. Okay, and